Welcome to section 6.1. This section is looking at angles, arc length, and circular motion. Our objectives for today are converting and actually knowing where angles are and their measure in degrees. Converting, like I had just mentioned, between decimals and degrees, minutes, seconds. These are two different ways that we can measure our angles. So we'll be talking about what these things look like and how to convert between the two. Find the length of an arc of a circle. So that's that outside part, the rounded part we're going to be looking at. Convert from degrees to radians and then back from radians to degrees. So again, we're actually going to be talking about, I think, 3 different ways to measure an angle. One is most common that you've probably seen before in degrees. The second is probably the least common, which is degrees, minutes, and seconds. And then the third is right in the middle, where you might have heard it, you might not have heard it, but we're going to talk about it today, and it's radians. Number 5, find the area of a sector of a circle. So if we only look at like one slice of pie out of a circle, then what would be that area of our one slice, kind of a thought. And find the linear speed of an object traveling in circular motion. So as something is moving around a circle, can we find the speed that it's moving at? These are some of the things that we're going to be talking about today. So let's jump in and talk about angles and degrees. As we take a journey around a circle, we know that these distances we have measured before in angles. And the angle just tells us how far apart are 2 of our lines, right? Let me try to get a more visible color. If I'm looking at maybe this line here going all the way up here, then the angle between them is something that we could measure. And we measure it in degrees, or we could measure it in degrees. That's one of our options. We can see that from here to here, this angle that's been created is a 60-degree angle. Another option would be if we went from here to here. This would measure the angle all the way around, going from here to here, and that would be a 240-degree angle. Now, if we go all the way around and end where we begin, then we would be going all the way around 360 degrees. So that'd be if you were standing in place and you turned all the way around to face exactly where you started from, you'd be spinning 360 degrees. These are degrees of measure. We are most commonly measuring with degrees. On this same diagram, you can see these values that have a pi in them. Those are called the radians. So all the degree measurements can also be written in radian measurement, and we'll get to that a little bit later. One of the important things that we should note is when we start here at 0 and then make any angle from our 0 degrees going out into wherever our angle is, we're creating this angle from our 0-degree spot, starting from 0 and moving outward. That kind of an angle has a special name. That's called standard position. So if you ever see something and it's asking about an angle in standard position, that's just an angle starting at 0 and moving its way out from 0. Something that might not be an angle that would not be in standard form is just if you had some random angle forming out here. It did not start at 0, so this one in orange went from 90 degrees up to 210 degrees. If I wanted to put that particular angle into standard form, then I would just grab one side and make it the 0, and then the other angle, let's see, 1, 2, 3. That one I will put in, I don't know, red. If this is where this angle started, then this is where my angle would end. So if I moved that orange angle into standard position, then it would become the red angle. And then I would be able to say, oh, well, that one has a measure of 120 degrees. I would not say that angle has a measure of 210 because it didn't start at 0. So that's the importance of using the standard position. Okay. So we talked a little bit about these degrees, and then I mentioned very briefly that there's degrees, minutes, and seconds, and that's just another way to measure angles. So just like we have degrees and just like we have radians, we also have this way to measure in degrees, minutes, and seconds. Now, just like when we have time on our clock, we have 1 minute is also the same thing as 60 seconds. And 1 degree is 360 seconds by that math. 1 degree represents 60 minutes, and then 1 minute represents 60 seconds. That's our biggest conversion helper, because if we want to convert from straight degrees into degrees, minutes, and seconds, we need to know, okay, how does our breakdown happen? Well, 1 degree is representative of this 60 minutes. We denote the minutes with one little apostrophe up there, and then we demote the seconds with 2. So as we get into from minutes to seconds, of course, we add another one. Okay, let's see how we convert with these. We have 2 problems here. Convert 19 degrees, 35 minutes, and 4 seconds to degree decimal form. So we're turning this form that's in degrees, minutes, and seconds back into degrees, so degree only. Well, let's break this up. We are seeing 19 degrees, 35 minutes, and 4 seconds. So I'm going to begin by writing that out. I have 19 degrees, and I also have 35 minutes, and I also have 4 seconds. And all together, these are going to come together to make 1 degree value, some kind of amount of degrees, right? So what do we know about minutes? Well, I know that 35 minutes is just the same as 35 times 1 minute. And I also know that 4 seconds is the same as 4 times 1 second. Now, why am I doing that? Well, because I know how these things are going to break down. I know how 1 minute makes 60 seconds. So that's very, very helpful to me to have it in units of 1. So I have 19 degrees, 35 times my 1 minute, because I had 35 minutes, so 35 times 1 minute. But I know that 1 minute is the same as 1/60th degree. Because up here, if we go back up here, 1 degree is 60 minutes. So if I have only 1 minute, that's a 60th of a degree. Plus 4. And one breakdown, this basic conversions table doesn't really show us, which might be helpful if you completed your guided notes. I highly recommend doing guided notes first. So if you want to pause this video and go and look through guided notes and then come back, I highly, highly recommend that. But one thing that I would take and add to this table is that 1 minute is 1/60th of a degree, and 1 second is 1/60th of a minute, which is 1/60th times 1/60th of a degree. And if you think about your value system, so if we look at our system of ones, tens, hundreds, we know that as we get smaller and smaller, we're dividing it by another 10 and dividing it by another 10. So in this case, we are dividing it by another 60 and dividing it by another 60. So we're working in almost this base 60 system. Okay, so back to our problem. We had 19 degrees plus 35 times 1/60th of a degree, which represents our minutes, and 4 times 1/60th times 1/60th, I keep doing that, 1/60th of a degree, which represents our seconds. Now, if we multiply these things out, we're going to get 19 degrees plus, and we have 35 over 60 is going to be about 0.5. And then 4 times 1/60th times 1/60th gives us about 0.001. And then these are all in degree form now, so we can just add them together. And that gives us 19.584 degrees. And we have successfully converted our degree, minute, and second form into degrees. Now let's go the other way. Let's go back from degrees into degrees, minutes, and seconds. And just as a side note, I'm going to put it over here on the side. We want to remember that 1 degree is 60 minutes and 1 minute is 60 seconds, because that's going to help us in our conversions. So we have 58.201 degrees. We want to turn this into degrees, minutes, and seconds. So to begin, I'm going to break it up between my whole number and my decimal, because 58 degrees, that's our degrees. Now we just need to figure out how many minutes and seconds do we have. So we have 0.201 that we are going to be converting into those minutes and seconds. So now I have 58 degrees plus a 0.201 times 1 degree. Why am I breaking this up? 201 times 1, of course I know what that is. Well, because over here I know what 1 degree is. So that helps me get closer to minutes and seconds. I can then update that. 0.201, 1 degree is 60 minutes. So how many minutes do we have? Well, let's find out. 58 degrees, 0.201 times 60 gives us 12.06 minutes. Okay, let's do the same process again. So now we have 58 degrees, 12 whole minutes, and let's find out how many seconds. 0.06 of a second of a minute. How many seconds is that? Well, I want to rewrite that. 58 degrees, 12 minutes, and then I'm going to have 0.06 times minute. Well, what is 1 minute? 1 minute is 60 seconds. 58 degrees, 12 minutes, 0.06, and I have 60 seconds. We multiply that out, and we'll find out how many seconds. 0.06 times 60, 3.6 seconds. This gives us about 58 degrees, 12 minutes, and 4 seconds. We'll just round it up. And so we have successfully gone from degrees, minutes, and seconds into degree form and back again. Back from degrees into degrees, minutes, and seconds. Okay. Next, we are going to be looking at the length of the arc of the circle. So we're talking about how we measure this angle here, but how would we measure that length around the circle if I wanted to know the distance instead of just the angle? Well, that's called the arc length. So it's the length of the arc. And we have a very nice, useful formula, which is S equals R theta. And each of these things, these variables, stand for an important part. The R represents our radius and the central angle, so that theta is the central angle, and it needs to be in radians. Radians is that way that we measure, it's our other measurement. Let me go back here. That we saw with these pi values. That is measurement of radians. So just like we measure with degrees, we also have these measurements in radians. And that is the measurement that we are going to be using in the arc length formula. So we have R is our radius, theta is our angle in radians, and that gives us our arc length represented by S. So let's use this formula to find these missing values. We have R equals 65 inches and theta equals 9 degrees. Okay, so before we begin, we already mentioned that our theta needs to be in radians. If this is something that you need to go back and read about, please do so. But you should know that 1 degree is pi over 180 radians. And if we wanted to go backwards, 1 radian is 180 divided by pi degrees. And pi is such a big part because we're working in circle. So we have our degrees, 180, we have pi because we're in a circle, and we're going back and forth between the two. In this particular example, our theta is in degrees, so we need to, in order to be able to use it, we need to turn it into radians. If 1 degree is pi over 180 radians, and I have 9 of them, that means in order to turn this into radians, I'm going to have 9 times pi over 180. So my formula is going to look something like this. S equals R times theta, and I'm looking for a radius of 65 and a theta of 9 degrees, which we have found out is going to be 9 pi over 180 in radian form. Now if I multiply all of this out, this will give me about 10.21 inches. Go ahead and put that through your calculator and double check me, but we're gonna get 10.21 inches. What does this mean? This means that this distance right here on this part of the circle, if my theta, my angle is only 9 degrees and my radius is 65 inches long, then this length around the circle, the distance around the circle that we've traveled is 10.21 inches. So it's really nice to calculate this. It kind of gives us an idea of if you were moving in a circular motion, how far would you go if you only traveled, 9 degrees around the circle. Okay, let's do it again. Let's find a different piece of information this time. So this time we have S equals 20 miles. That right there means that we've traveled 20 miles around our circle and our radius is 18 miles. So thinking about this, we're dealing with a huge circle. It's probably unrealistic for us to get out and actually make this circle, to actually have a radius of 18 miles and we're traveling 20 miles around one fixed point. So in real life, unrealistic to do it, but in a math class, we can calculate. We can figure out, okay, what would the degree be rotated around this one point? We can calculate that without actually having to do the actual real experiment in miles, which is really nice. We don't even have to leave the comfort of our chair to calculate these. So we're going to stick to our same formula. S equals R theta. We have S of 20 miles, so I'm going to replace my S with a 20. My R, my radius, is 18 miles, and it looks like this time we're looking for that theta. We're looking for that angle. What is it going to be? Well, if I want to get theta alone, I'm just going to divide that 18 away. And whatever I do to one side of my equal, I have to do to the other, which leaves me with theta equals 20 over 18, which is approximately 1.11. And that's going to be the degrees of our angle. So this is a humongous circle. If you think about that, I've only gone 1 degree and I traveled 20 miles. This circle is humongous. So thankful we can calculate without actually having to work them out physically, traveling 20 miles for 1 degree. Okay, now we already started this, but I want to dive deeper into converting the degrees and radians and back and forth. So just like we said before, if we want to go from degrees to radians, then we will take our degrees and multiply it times pi over 180. That will give us our radians. And if we want to go from radians to degrees, we take our number of radians and times it by 180 over pi, and that will give us our degrees. So this is a nice little handy formula, two formulas that we can use to convert to whatever we need. Some of the things we're calculating, we only need degrees. Some of them, we need it in radians. And being able to convert back and forth is very useful. So let's do it. Let's convert 630 degrees to exact radians. Exact is the key word here. We do not want to estimate. We do not want to round. We want to leave it exactly, so that way we are not estimating. Whenever we round, we begin to estimate. So we're leaving it exact. We're not going to work any fractions out. We're going to leave it in fraction form. And since we're dealing with a pi, we are leaving pi in there. So in order to convert from degrees to radians, we take our degrees and we multiply it times pi over 180, which will give us 630 pi over 180. Now you can reduce 630 over 180, reduces actually pretty nicely to a 7 over 2. And we still have pi there. We're not moving with the pi. So this is a fraction answer. We have our pi in there. We haven't changed anything. We just reduced. That is our exact answer right there. As soon as you throw it in your calculator and you get a decimal and you round it, now it's an estimate. This, as a fraction with pi in it, is still an exact answer. And that's where we stop. Now, let's take a look at 61 degrees to a decimal radian. This one we will throw in our calculator and we will get a decimal out. So we take our degrees and we multiply it times pi over 180 because we're going to radians, which will give us about, this gives us 61 pi over 180. Now if you throw that through your calculator, then you should be getting a decimal, which will be about 1.06. And this is our radians. And we can also go from radians to degrees. And we use the other formula, which is the reciprocal. So we take our radians, 0.92, and we multiply it times 180 over pi to go back to degrees. Now if we multiply this out, we have 0.92 times 180 all over pi. That will give us about 52.71 degrees. Being able to go back and forth from radians to degrees is a very helpful thing, especially in this pre-calculus course. I highly recommend writing these down, doing some practice problems, and getting used to going back and forth between the two, getting comfortable with the terms degrees and radians. Okay. Our next objective is to find the area of a sector of a circle. So we've talked about this, how we measure the degree of an angle. We've talked about how to get the distance around our circle. But what we want to talk about now is this area. So maybe we're only covering this part of a field with carrots. We need to know what area is covered in carrots. That's where the area of a sector comes in. We're looking at just this one sector here. We're going to find the area of it. So how do we do that? Well, we have a nice formula for the area of a sector. The area of a sector is represented by A equals 1/2 r squared times theta. A being the area, r being our radius, and theta being that measure, that angle that we've been working with. When it tells us theta, we can automatically begin thinking, okay, I'm dealing with an angle. This one is called our central angle because we're dealing with the angle that's being formed out of the center of our circle. So here we have a circle with a radius of 50 inches and a central angle of 1/4 radians. In order to find our area, we will just use this information in our formula. So our area is going to be 1/2 times r squared, so our radius squared. In this problem, our radius is 50 inches. So r squared would be 50 squared. And our theta is 1/4 radian. So our theta is 1/4. Notice that we didn't change our radian measure into degrees because our theta is measuring in radians. We're using radians in our theta. Okay, so now we can multiply these out. This gives us 50 squared over 8. If we multiply straight across, and 50 squared over 8 is going to give us 312.5. And since this is an area and we're measuring in inches, it's inches squared. So that would be the area of this section of the circle if the radius was 50 inches and the angle was 1/4 radian. Now, we're just going to continue our discussion on these circles and talk about something maybe moving around the circle. It's traveling in a circular motion, and we want to know what is the linear velocity. So we can see by this picture here that this green ball is moving around this circle. It's moving in circular motion. You can see all these arrows coming off of it, and you can think of the linear velocity almost as if it were released. Where would it be going? It would be going that way. You know, at what point, if it was released at one of these points, it's going to go that way. So, how do we find out what it is? Well, luckily, we have been given some beautiful formulas to help us. For our linear velocity, our linear speed is what the text calls it. We have a formula of V equals S over T. Now, notice our S is familiar. We've seen that before. S, remember, is the same thing as R times theta. Let's go back. If you're thinking, wait, what? What are you talking about? Where did we see that before? I'm going to bring you all the way back to finding the length of an arc. Well, here we have our formula for finding the distance, right? That arc length, and that was the radius times theta. That S is the exact same S we are going to be using down here to find our linear speed. The S that we're talking about is that distance that it's traveled around the circle, and we're just dividing it by the time that it took. So let's start with that, because our question wants us to find the linear and the angular speeds. So we have two pieces to look at. Let's talk about our linear speed first. We said that our linear speed is taking the arc length and dividing it by the time. Well, we know we can rewrite our S. Arc length is R times theta. We know that from our practices before. So now let's use the information that they've given us. A radius, the object is traveling around with a radius of 8. So that's what I'm going to plug in for my R. And theta, 1/3 radian, is our central angle. So we have 1/3 is our radian. And our time, it did this in 40 seconds. So we've plugged everything in. Now if we 8 divided by 3 divided by 40, we put that in our calculator, we're going to get something similar to 0.067. Now we were looking at speed. This was our linear speed, our linear velocity. So we measure speed in distance and time. So this is measured in, we have inches, and we have seconds. So we have gone 0.067 inches per second. Now, we want to find our angular velocity. Now, the angular velocity is very similar to what we've been looking at, but now we're going to use this formula right here. We have lowercase omega representing our angular velocity, and this is measured in radians per our time. So we've got our theta in radians and our time. Just as you would suspect, now we're looking at, okay, what is the angular speed? Which brings in that the radians and time tie-in. Using our lovely formula, we have omega equals theta over time. And we know, based on what they've given us, our theta is 1/3 radian, and our time is 40 seconds. And if we divide 1/3 divided by 40, it's going to be approximately 0.0083, and this is again radians per second. And we found both of our different speeds of this particular object. And that's all we have for section 6.1. Again, I encourage you to complete your guided notes and complete your homework assignments and discussion questions, and ask your instructor if you would like any further clarifications. But to summarize, we're really getting comfortable with measuring these angles in degrees, radians, and minutes and seconds, and then using different formulas to find information about what's happening in our circles.